Our observable universe extends precisely 46.5 billion light-years in every direction from Earth. This number represents the cosmic horizon of our potential observation, everything that could theoretically be detected from our vantage point since the beginning of time. This 46.5 billion light-year radius often confuses astronomy enthusiasts. The universe is only 13.8 billion years old. So how can we possibly see something more than 13.8 billion light-years away? The answer lies in cosmic expansion. While light from distant objects has been traveling for at most 13.8 billion years, the space between us and those objects has been stretching continuously during that journey. The most distant light we can detect left its source when that source was much closer to us than it is now. Think of the universe as an expanding balloon with ants on its surface. Two ants might start an inch apart, and one sends a signal toward the other. As the balloon inflates while the signal travels, by the time it reaches the second ant, they could be several inches apart, though the signal only traveled what was originally 1 inch. The cosmic horizon represents a fundamental barrier to direct observation. This limitation isn't technological. No matter how powerful our telescopes become, they cannot detect what lies beyond this threshold. Light from objects beyond the cosmic horizon simply hasn't had enough time to reach us since the universe began. While our observable universe grows larger as time passes, as light from increasingly distant regions finally reaches us, some galaxies we can see today will eventually disappear from view. The universe's expansion is accelerating, driven by dark energy. Galaxies sufficiently far from us are receding faster than the speed of light due to expanding space itself, which means their light will never reach us again once the photons currently on their way have arrived. Within our current observable sphere exists approximately 2 trillion galaxies. Each contains billions of stars, possibly trillions in larger specimens. The Milky Way alone houses between 100 to 400 billion stars, with recent research suggesting it may contain up to 1 trillion. Astronomers suspect this vast collection represents a minuscule fraction of what exists beyond our cosmic horizon. Modern observatories like the James Webb Space Telescope can peer almost to the edge of this boundary, capturing light from galaxies as they appear just a few hundred million years after the Big Bang. These technological marvels let us glimpse the universe's infancy, but they operate within the same constraint. They cannot see beyond our cosmic horizon. This edge of our observable universe isn't a physical boundary like a cliff edge. There's no wall, no barrier, no dramatic change in the universe's properties at this distance. It's a limit imposed by the finite age of the universe combined with the speed of light. If the universe were infinitely old, our observable region would be infinitely large. But since the cosmos has a beginning, our observation has a boundary. This boundary creates a relationship between distance and time in astronomy. As we look deeper into space, we're simultaneously looking farther back in time. Light from nearby Proxima Centauri shows us this star as it was 4.3 years ago. Light from Andromeda reveals this galaxy as it existed 2.5 million years in the past. The most distant detectable galaxies appear to us as they were billions of years ago, primitive cosmic structures in the universe's youth. Our image of the universe becomes progressively more outdated as we look farther away. The most distant observable galaxies may no longer exist in the forms we see them. They had billions of years to merge, evolve, or be torn apart by cosmic processes while their ancient light journeyed toward Earth. The expansion of space complicates this picture. Objects whose light we detect from billions of years ago were substantially closer to us when they emitted that light than their current physical positions. The 46.5 billion light-year radius represents how far away these objects are now, accounting for all the expansion that's occurred during light's journey. Consider the cosmic microwave background radiation, the oldest light in the universe, released about 380,000 years after the Big Bang. This radiation comes from every direction, forming the most distant observable surface in our cosmic vision. The sources of this radiation were relatively close when they emitted this light, about 42 million light-years away. However, those same regions have now been carried approximately 46.5 billion light-years away by cosmic expansion. The 46.5 billion light-year radius helps us understand why the universe appears remarkably uniform on large scales, despite regions on opposite sides of our observable universe having never been in causal contact with each other. This horizon problem became one motivation for cosmic inflation theory, which suggests the universe expanded exponentially in its first fraction of a second, allowing regions that now appear disconnected to have once been close enough to establish equilibrium. Each observer in the universe has their own unique observable bubble centered on their position. An alien in a galaxy 10 billion light-years from Earth would see a completely different set of galaxies at their cosmic horizon than we do at ours. Their observable universe would contain many galaxies forever invisible to us, while missing many that we can see. This concept of observer-dependent cosmic horizons reinforces a profound truth. The universe doesn't have a center in the conventional sense. Every point can be considered the center of its own observable universe, with space stretching in all directions around it. The 46.5 billion light-year radius isn't measured from some privileged central point in the cosmos, but rather from any observer's location. Measuring the unmeasurable. That 46.5 billion light-year radius presents a mind-bending cosmic puzzle. How could light possibly travel more than 3 times the distance expected given the universe's age? This isn't a mathematical error. It's a profound clue to understanding spacetime's dynamic nature. To grasp this apparent contradiction, we need to completely reconsider what distance means in an expanding universe. The key insight is that conventional distance calculations break down on cosmic scales. The universe's age of 13.8 billion years would suggest our observable universe extends only that far in light years. Yet astronomers confidently measure 46.5 billion light years. This discrepancy reveals a fundamental misconception about cosmic distances. Space itself is expanding. When astronomers observe ancient light from the universe's first galaxies, they're seeing objects as they appeared billions of years ago. During those billions of years, the space between those galaxies and us has been stretching continuously, like marks on a rubber band being pulled apart. The marks themselves aren't moving through the rubber, but the increasing distance between them creates greater separation. Consider a galaxy whose light has been traveling to us for 13 billion years. When that light began its journey, the galaxy was much closer, perhaps only a few billion light years away. But during those 13 billion years, space expanded dramatically. By the time we receive its light, the galaxy has moved to a present-day distance of over 30 billion light years, despite its light traveling for 13 billion years. To measure this expansion precisely, astronomers rely on redshift. As light travels through expanding space, its wavelength stretches, shifting toward the red end of the spectrum, similar to how an ambulance siren drops in pitch as it moves away. The greater the redshift, the more space has expanded since that light was emitted. By analyzing the redshift of thousands of galaxies, scientists have constructed a detailed expansion map throughout cosmic history. This expansion started rapidly after the Big Bang, slowed as gravity pulled matter together, and then mysteriously began accelerating about 5 billion years ago due to dark energy. Measuring this complex expansion history required multiple innovative techniques working in concert. In the 1990s, astronomers made a breakthrough by studying type I supernovae, stellar explosions that function as standard candles with consistent peak brightness. By comparing their apparent brightness from Earth with their known intrinsic brightness, scientists calculate distances with remarkable precision. Type I supernovae provided the first clear evidence that the universe's expansion is accelerating, explains Dr. Adam Rees, who shared the 2011 Nobel Prize for this discovery. We found distant supernovae were dimmer than expected in a universe where expansion was slowing down or remaining constant. Building on these findings, scientists turn to the cosmic microwave background radiation. Its tiny temperature fluctuations create acoustic peaks, regions where primordial sound waves compressed the early universe's matter. The size and spacing of these peaks reveal critical information about cosmic geometry and expansion history. These measurements were further refined with baryon acoustic oscillations, BAO, massive sound waves that traveled through the early universe's hot plasma before freezing into place. These oscillations created a characteristic pattern in galaxy distribution, with slightly more galaxies separated by about 500 million light-years. By measuring this pattern at different cosmic epochs, astronomers track how space has stretched over billions of years. The mathematical framework for understanding this expansion comes from Einstein's general relativity and the Friedmann equations derived in the 1920s. These equations allow cosmologists to work backward from current observations, reconstructing the universe's entire expansion history with remarkable precision, arriving at the 46.5 billion light-year radius. What strengthens scientists' confidence is how these independent measurement techniques, supernovae, cosmic microwave background, and baryon acoustic oscillations, converge on the same expansion history. Together, they form the consensus Lambda CDM Model, which precisely defines the universe's composition. About 68% dark energy, 27% dark matter, and 5% ordinary matter. This model enables astronomers to calculate our observable universe's radius without ever directly seeing its boundaries. The calculation considers not just the universe's age, but also the changing rate of expansion throughout cosmic history. The result, 46.5 billion light-years, represents one of humanity's most remarkable measuring achievements. This measurement continues to evolve as the universe expands. Our observable bubble grows too, not because we can see farther, but because space itself is stretching. Yet, counterintuitively, many currently visible galaxies will eventually disappear from view. The accelerating expansion means light from these extremely distant galaxies will never reach us again. They're being carried away faster than their light can travel toward us. This raises profound questions. What lies beyond our observable universe? Are there regions of space we'll never be able to detect? How does this expansion ultimately determine the fate of cosmic structures? These questions highlight how measuring cosmic distances isn't just about defining boundaries. It's about understanding fundamental limits of knowledge in an expanding universe. We're not limited by our instrument's power, but by the physics of an expanding universe. Even with telescopes millions of times more powerful than James Webb, we can never see beyond our cosmic horizon because light from those regions simply hasn't had time to reach us yet.